This is project 2, video number 2, the one in which we code up the program. So I fired up MATLAB already. I'll get into the editor. I want to go with function, create a function. It returns nothing, so I'm going to call the dummy variable dummy, or the return variable dummy. And what am I doing? I'm graphing the power. Dissipated in resistor R2, but graph power is enough. Takes no arguments. And I'll put the end there for end in the function, tab over so that the contents of the function are indented. And then I'm supposed to start out by initializing variables v, R1, and R2. So capital V equals 28 volts. R1 equals 44 ohms. R2 equals 22 ohms. And then my next step, the plan was create R3, the array. R3 equals linspace 0, 200, and I wanted 101 of them. And then evaluate these equations. So let's try doing that. Equation 1 is R23, so that parallel combination of resistors R23 equals 1 divided by the quantity 1 over R2 plus 1 over R3. Alrighty. I'm working with an array here, so I got to do a lot of these mathematical steps on an element by element basis. I'm going to just type in the math and then fix that up later. So I got to use a dot slash there instead of a slash, for instance, but I prefer to go back and fix that. So I just am thinking about getting the equations in correctly at this stage. So the next one is R total is R1 plus R23. R tot equals R1 plus R23 semicolon, then what? R equation 3. When I go to the next one, it's supposed to be coming down to here. There it is. I is V over R total to get the total I. Semicolon, so I didn't print it out. Then that was I, and then I'm coming up to here. Equation 4, V23 is equal to IR23. V23 equals I times R23. Put a semicolon on there. And then V2 is V23. And then I2 is V2 over R2. And then the power. I2 equals V2 over R2 and then P2 equals I2 times V2. Okay, let's see. Just have to plot. Oops, lowercase. Plot. Now I'm plotting P2 versus R3. So I put R3 first, the independent variable, and then P2. Alright. So let's see what happens. I'm going to save this baby as graphpower.m. Close the original first. So window, graphpower.m. Close that baby. That was an old version that I was working on a little while ago. So let's try saving it again. So file, save as graphpower.m. This time it saved it. So this should be the function I just wrote. That's the only one that'll be there. So let's try running that. Graphpower. Open, close. And oh, I said I was going to go back and fix all that stuff, so it's all messed up because I'm treating this array, the R3, as if it were just a number. So that was nice of the computer to let me know about that. So 1 divided by an array, that then creates an array. Here I'm just adding a number to it. Whenever R2 is just a number, so you can add a number to an array. It automatically adds a number to every element in the array. And then that forms this array down here in parentheses. So if I want to take the 1 divided by that, I got to use the dot. Remember, the dot slash means divide on an element by element basis. So that's when I get an array and I want to do it on an element by element basis, that's what I got to do. Here, this is an array now, and I'm just adding a number to it, so that's no problem. Our total is an array. Dividing by an array, so I really want to divide on an element by element basis. So now that creates an array I, and now I'm multiplying one array times another. So R23 is an array, and so is this, so I need dot star just instead of just star to do it on an element by element basis. Just assigning an array to another array. And then R2 is just a number. That's interesting. So I'm dividing every element in the array V2 by the pure number R2. So that's no problem. Just it's like multiplying by a scalar. R2 is my scalar, so don't need a dot star for that. And then I'm taking the result and I think I'm multiplying 2 arrays here. So V2 is an array and I2 is an array. Yeah. So I need the dot star there, and then I'm plotting P2 as a function of R3. R3 is an array, P2 is an array. So let's try that again. Save it. Run it. This time I don't seem to get any errors, but rather than that I get a graph. Kind of interesting. It starts out with a relatively small slope that gets steeper, and then it's getting steeper and steeper up to about here, and then it starts getting less and less steep for the rest of the way. But it's monotonically increasing, so the power is always increasing. That is, the bigger R2 is, the bigger the power. I'm sorry, the bigger R3 is down here, the bigger the power dissipated in R2. Let's see if that makes sense. think this isn't part of the pencil and paper here, pencil and paper solution. But I do want to see if we can make some sense of what that's saying. So P2 is equal to that. I want to do some back substitution to see if we can see what's going on. To see if, indeed, it seems like as R3 increases, the power through R2 should increase. Alright. This we can just write as, I can replace either one of these. I think I'll put I2 in there. So P2 goes like V2 squared over R2. So as goes V2 squared, so goes P2. In other words, the bigger V2 is, the bigger the power is. So if V2 increases as R3 increases, then we got it made. Let's see if we can get V2 as a function of R3 is equal to I times R23. So from here, and then I'm going to try I is V over R total. So V2 V over R total is R23. So this is V2 is V over R1 plus R23 times R23. I think I'll divide top and bottom by R23. That's equal to V divided by R1 over R23 plus 1. So R23 into the top just gives me 1 up there. R23 into the bottom gives me this. So constant, constant, constant. The only thing that's changing is R23. R23 is equal to 1 over R2 plus 1 over R3. So here's the deal. If R3 goes up, then that makes this number, it gets bigger. So this piece that I'm adding onto here gets smaller. The bigger R3 is, the smaller this piece is that I'm adding onto this constant. So the bigger R3 is, the smaller the diameter, the smaller the denominator. Got it? The smaller the whole denominator. Bigger, as R3 goes up, the denominator gets smaller. This whole denominator in parentheses. And so I'm dividing that into 1. The smaller the denominator, the bigger the fraction. So if R3 goes up, R23 goes up. From looking at this equation. And then if R23 goes up, then what happens to V23? R23 is in the denominator of this little fraction, so R23 increases, makes this smaller, so that makes this whole denominator smaller. It being in the denominator, it makes V23 greater. So V23 goes up, and that's from this equation. if V23 goes up, then V2 goes up. Yeah, probably. I think I was already using the fact that V2 is equal to V23. So let's just call this V2 goes up. And then if V2 goes up, P2 goes up from this equation up here. R2 is a constant. So if V2 increases, P2 increases. And again, I use the fact that V2 is equal to V23, so V2 is equal to all this stuff. That was just a mistake to be writing that down as V23 at that stage. It's true, but from the line above, I should have copied it down as V2. So, finishing it off, P2 goes up. So I do expect that P2 goes up. With all these things being in the denominator, I wouldn't expect it to be linear, but it's clear that if R3 goes up, P2 goes up. So that represents a check on our work. And it suggests that it doesn't prove that this is right, but at least it's got the right kind of behavior. That is, it's increasing as R3 gets bigger, the power dissipated in R2 increases. Okay, we better call that a wrap for Project 2 video number 2.